Okay, this is section 16.5, weak acids and acid dissociation constants. So we looked at strong acids in the previous section. Now we're going to look at weak acids. And it turns out that there are many acids found in nature in which the acid dissolves in water, but it reacts with water to a much smaller extent. In a sense, it's less reactive toward water than the strong acids are. And so we get essentially the same equation as we would with a strong acid, except that note that I put the double arrow here for the equation. That tells us it's a reversible reaction and that we're going to apply chemical equilibrium principles to this particular problem. Okay? So the equation looks the same except for the double arrow. Essentially what happens is only a small percentage of the acid actually reacts with water to form hydronium. Most of the acid is unreactive. So if this is the case, then what we'll do is we'll define something called the acid ionization constant. It's an equilibrium constant, just like any other equilibrium constant. But we'll use a subscript A to indicate that this is the acid ionization constant. And it is the concentrations of the products multiplied together. So it's really a Kc, right? Not a Kp. We're not talking about gases. So hydronium times the counterion, or the conjugate base, divided by the concentration of the acid itself. Okay? So there's our acid ionization, sometimes called acid dissociation constant. If you look at table 16.6, there is a list, a very abbreviated list of a few of the common weak acids, but this is by no means an exhaustive list. There are thousands of weak acids found in nature. Those of you who are biology majors are familiar with many of them. The amino acids are weak acids, for example. Okay? And so hydrofluoric acid has a Ka value, these are all taken at 25 degrees C, of 7.1 times 10 to the negative 4. Another common weak acid is acetic acid further down the list. Acetic acid has an acid ionization constant of 1.8 times 10 to the negative 5. So that list is in the order of largest Ka to decreasing Ka values down to the lowest value in this list is phenol. Again, this is not an exhaustive list. This is just a few selected. It really should say selected ionization constants. So Ka values are, generally less than 1. They can be relatively small values here, and those are what we're going to use to do many of the calculations in this particular section, and that will lead us into all sorts of different acid-base problems where we need to know the values of the acid ionization constant for particular acids. Okay, so what I'm going to do is I'm going to show you the first type of problem. And the first type of problem is the case where we're going to calculate the pH of a weak acid. Okay, so we're going to figure out what the pH of a weak acid is. The weak acid that we're going to pick is hydrofluoric acid, and the initial concentration of the hydrofluoric acid is going to be 0.50 molar. Okay, 0.50. So here's what we're going to do. We're going to say we want to find or calculate the pH of a 0.50 molar HF solution. This is the first type of problem. Now, when you do these problems, if you want to find the pH of a weak acid solution, you need to know the value of the Ka. So notice in the table, 16.6, it's there. 7.1 times 10 to the negative 4. So you're going to use that value. And here's how you go about it. What you do is you say, we know the initial concentration of HF. This is the initial concentration. And we know the value of the Ka, because we can look it up in this table. Okay? So what we do is we write out the chemical equation for the acid reacting with water. And it's a weak acid, so it's reversible. If this were a strong acid, you just write the forward arrow. Forms hydronium. And then the conjugate base would be the fluoride ion. And then you set up an ice table. So the initial concentration of HF is 0.50. Water we're not going to worry about because water is a liquid and liquids are not involved in the equilibrium expressions. We're going to assume that these are initially 0. And then we do our Q calculation, right? Reaction quotient. So Q would be the concentration of hydronium times the concentration of fluoride divided by the concentration of HF, which would be 0 times 0 over 0.50, which is 0. So Q is less than K. So the change that we would have would be to the right. So we lose reactants, and we gain products. And then at equilibrium, we're at 0.50 minus x, 0 plus x, and then 0 plus x. So now what we can do is we can say that Ka is the concentrations of the products, x times x, divided by the concentration of the reactant, which is 0.50 minus x, and that is equal to 7.1 times 10 to the minus 4. Now, what we will do is we're going to try to find the pH. The pH is the negative log of the hydronium concentration. The hydronium concentration is x, so all we need to do is figure out what x is and then take negative log of that. Okay? So how do we solve for x? Well, it looks like a quadratic formula type problem as we saw back in chapter 15. But what I'm going to do is I'm going to make an assumption here. And the assumption I'm going to make is that, I'm going to write this down, this is an assumption, is that 0.50 minus x, that's the denominator of that expression for Ka, is approximately equal to 0.50. Now, we'll test the validity of that assumption later, but this is a very common method that we use in acid-base chemistry, is that we assume that if an equilibrium constant is small, meaning much less than 1, and Ka is much less than 1, right? It's only 7.1 times 10 to the minus 4. We make the assumption that the initial concentration of the acid minus x is essentially equal to the initial concentration. Okay? What that does is it simplifies the expression dramatically. We now have an expression that says that Ka is x squared over 0.50. That's a lot easier to solve for x, because now all I have to do is multiply Ka by 0.50, and that gives us x squared, and then take the square root of both sides, and that gives us x. That's pretty nice. That's just the square root of 7.1 times 10 to the minus 4 times 0.50. Well, that's the square root of 3.55 times 10 to the minus 4. Okay, so let's check, see what that is. 3.55 times 10 to the minus 4, we're going to take the square root of that. So 3.55 times 10 to the minus 4, and we want the square root of that, 0.0188. Okay, since x is equal to the concentration of hydronium at equilibrium, pH is the negative log of that. Oops, 1.88 times 10 to the minus 2. Okay, let's figure out what that is. So there's our number, so let's take the log of it, and then multiply it by minus 1. And you get 1.72. And there's our answer, 1.72. Okay? We figured out the pH of a weak acid by using this ice table, just like we've done with other problems in chemical equilibrium. Okay? Now, suppose that we had not made the assumption. Suppose the assumption we didn't do that, so we used the quadratic formula to solve for x. It turns out you would have gotten a very slightly different number. You might have got about 0.019 for x, and then pH 1.71 or 1.715 for the pH. Very small difference. So it's actually a pretty good assumption. Okay? Now, one question comes up is, when do you know whether you can use that assumption? It is a nice one. It turns out most of the time you can use it with weak acids because the values of K are small. But here's what we would say. What we would say is you calculate X. And then divide X by the initial concentration of the acid. And then convert that to a percentage. Not 1,000%, sorry. 100%. Okay, and once you do that, if it's less than 5%, then it's an appropriate assumption. And if it's greater than 5%, it's inappropriate. So that means you would have to use the quadratic formula. Okay, so it really just comes down to that. Most of the time, it's a good assumption. The few times where it's not good are if the Ka value is closer to 1, like 0.1 or 0.01. That's a pretty large Ka. Or if the initial concentration is very, very small. Okay, so let's check it for this one. What it said was you take X, you divide that by the initial concentration. So for X, we had 0.0188. Divide that by 0.50, and then multiply that by 100%. And it turns out if you do that, you get about 3.8%. 3.8% is less than 5%, so that means it's a good assumption. And so our answer, pH 1.72, would be the correct answer. Okay? So that's the first type of problem that we see in this section, is determining the pH of a weak acid given the initial concentration of the weak acid. Okay? And it's an equilibrium problem, right? So there's one difference, is that with weak acids we use equilibrium techniques, whereas with strong acids we don't have to do that. Okay? The second type of issue that comes up is when we want to calculate the pH from Ka. So, I'm sorry, let me re-express that. The second type of problem is when we want to calculate percent ionization. So I'll write this as 2% ionization. Percent ionization is a very simple issue. What you're doing is you're calculating the concentration of hydronium once the solution is at equilibrium, divided by the initial concentration of the acid times 100%. It's just a different way of reporting the answer to what we did in the previous problem. instead of saying, oh, the pH is 3.25 or the pH is 1.72, we're saying what percentage of the acid actually formed hydronium. Okay, so imagine if you have a mole of the acid and 0.1 moles of the acid is converted into hydronium. You would take 0.1, divide that by 1, and multiply by 100, and you would find out that 10% of the acid was converted to hydronium. Okay, so you calculate what the hydronium concentration is, you divide that by the initial concentration, and multiply that by 100. Okay, so let's try an example of this. The one we're going to use is acetic acid with a concentration of 0.1 molar. So let's calculate the percent ionization, percent I I'll call it, for, benzoic acid. I'm doing the problem right out of your textbook. And if you look at the table, benzoic acid is right in the middle, 6.5 times 10 to the minus 5. So it has a Ka of 6.5 times 10 to the minus 5. When the initial concentration is 0.10 molar. Okay? Calculate the percent ionization for benzoic acid. Benzoic acid has a Ka of 6.5 times 10 to the minus 5 when the concentration is 0.1 molar. So in other words, we're making a solution of benzoic acid with a concentration of 0.1 molar. Now, if you look at the chemical formula, it's a pretty big chemical formula there. It's C6H5COOH. But the same idea, you react it with water, donate the H plus to the water to give you hydronium, and take the H plus off to get the conjugate base. Okay, so there's your equation for that one. Okay, the initial concentration of benzoic acid is 0.1 molar. Water we don't worry about. These are initially 0. Again, Q is equal to 0, so the reaction goes toward the products to the right. So minus X, and plus X. And then at equilibrium, 0.10 minus X, X and X. So notice that this is done just like the pH problem, because really what we're going to do is we're going to find X, and then X is going to be used to find the percent ionization. So here's how we approach it then. We say, okay, let's take our Ka value, which is known. That is equal to the products over the reactants. So X times X divided by the reactants, 0.10 minus X. Okay. Now, we could go through and punch this through and then solve using the quadratic formula, but let's use the same assumption that we used in the previous problem. The assumption is that if we substitute 0.10 in the denominator for 0.10 minus X, we'll get about the same answer. So this is approximately equal to X squared over 0.10. It's going to be pretty close. Okay? So solve for X. That's the idea here. With weak acids, that's generally what you end up doing. You solve for X. So X squared, I'm going to multiply both sides by the denominator, 0.10. Okay, well that's easy. That's 6.5 times 10 to the minus 6, right? And then X would be the square root of that. Six 6.5 times 10 to the minus 6. Okay, there we go. Square root of it. 2.55 times 10 to the minus 3. Okay, so if we wanted to find the pH, we would just take the negative log of that, but we're doing a percent ionization problem. So in percent ionization, you come back to that formula. Hydronium concentration at equilibrium divided by the initial concentration of the acid times 100. It's actually the same formula we just used when we were doing the test to see if the assumption was good. And we'll actually see whether it's a good assumption here as well. So hydronium concentration is X, so that's 2.55 times 10 to the minus 3. Initial concentration was 0.1, and then times 100%. Now this is one I can do without the calculator, and here's why. If you multiply by 100, that just makes it 2.55 times 10 to the minus 1. If you divide by 0.1, that makes it 2.55 times 10 to the 0, or just 2.55%. And there's our answer, 2.55%. So you can actually go back and you say, well, wait a minute, was it a good assumption that 0.1 minus x is equal to 0.1? Well, the percent ionization is also a measure of how much of it dissolved, and it was under 5%. So yes, good assumption. It's a decent assumption there. 2.5% is the amount of the acid that dissolves. So what that's telling us, or ionized, not dissolved, but ionized. What that's telling us is that the rest of it did not react. In other words, the benzoic acid, 97.45%, right? 100 minus 2.55, that amount didn't react. It's dissolved in the water, but it's unreactive toward the water. So only a small percentage of the benzoic acid reacted. Okay? Now, what would happen if we changed the initial concentration? Suppose that instead of making it 0.1 molar, we made it a little different, like 0.05 molar. Okay? So I'm going to erase some of this work here. I'm not going to go through the problem with you. Your textbook does it, but I'm just going to mention the result. Suppose instead of 0.1 molar is the initial concentration, suppose we used 0.05. What would happen is you would end up with an expression of Ka is x squared over 0.05 minus x, which would be approximately equal to x squared over 0.05. Okay? So if you then plugged it in, you would have x is equal to the square root of 0.05 times 6.5 times 10 to the minus 5. And that's 3.25 times 10 to the minus 6. So if you take the square root of 3.25 times 10 to the minus 6, you get 0.0018. So now there's your x, that's your hydronium concentration. So if you do a percent ionization here, it's 0.0018 over 0.05 times 100%. So let's try that, 0.0018 over 0.05. .61. Look what happened here. The initial concentration was less in this example than it was in the previous example. In the previous example, it was 0.1 molar, right? That's over here. If we change the initial concentration to a lower value, the percent ionization goes up. It increases. So that's one result that you should be aware of, which is that the lower the initial concentration of the acid, the higher the percent ionization. Sorry, lower initial concentration of the acid, the higher the percent ionization. Okay? So if you made the initial concentration really, really, really small, a large amount of it would ionize. Okay? And so Higher initial concentrations result in lower percent ionizations. Okay. The last type of problem we're going to look at in here is how do we figure out the value of Ka from a measurement of pH. So let me show you what I mean by that. In this type of problem, this is the third type of problem, we're going to measure pH, and from that, we're going to calculate Ka. Okay, let me show you how that works. The example that your textbook gives is they give you a hypothetical acid they call HA, and it has an initial concentration of 0.25. So let's say we have an acid, it's a weak acid. We'll call it HA. And the initial concentration is 0.25 molar. And then they measure the pH using a pH probe. And they find it's 3.47. Calculate Ka. Okay, that's the third type of problem. You're given the initial concentration, 0.25 molar. You're told it's a weak acid. You're given the value of the pH, and you go back and you calculate Ka. So here's how you go about it. It's an ice table again. So you say HA is going to react with water. It's a weak acid, so it's reversible. Hydronium and A- is the conjugate base. We know the initial concentration of the acid, 0.25. Again, we don't worry about water because it's a liquid. These are initially 0. Now, all we know other than the 0.25 molar is the pH. What does that tell us? Well, here's what I'm going to do. Since these are initially 0, Q is equal to 0. So we do know this is going to go down by some amount, and this will be 0.25 minus X, right? And these will go up by some amount, and so at equilibrium, they'll both be X. Here's what we do. Notice that at equilibrium, hydronium is X, and the conjugate base A negative is X. Well, pH is the negative log of hydronium. So in other words, the pH is actually going to tell us what X is. The concentration of hydronium is 10 to the negative pH. We learned that in an earlier section, right? So that's equal to X. But not only does that give us hydronium X, it also gives us the conjugate base X. It actually gives us both of those, and it gives us this one over here, the amount of the weak acid that actually ionized. So we can now find the equilibrium concentrations of everything, plug them into the expression Ka is X times X, or X squared, over 0.25 minus X. So we just got to find out X that way. So here it would be 10 to the negative 3.47. Okay, so let's use our calculator to find that. 10 to the negative 3.47. Okay, so we're going to do 10 to the X. 3.39 times 10 to the minus 4. There you go. So now we can say, okay, well, it's X squared over 0.25 minus X. So that would be 3.39 times 10 to the minus 4 squared over 0.25 minus 3.39 times 10 to the minus 4. Okay. So let's figure out what 3.39 times 10 to the minus 4 squared is. So I'm going to square this. And then I'm going to divide it by 0.25 minus 3.39 times 10 to the minus 4. And there you go. 4.59. Let's round that to 4.6. 4.6 times 10 to the minus 7. There's our Ka, right? So look at this problem. This is our third type of problem. We are given the initial concentration of the acid. We're given the pH. The pH, by using hydronium, is 10 to the minus pH. That gives us this value here. It gives us this value here. And it also gives us this value here. So once you find out what X is, you plug them back into the expression here. And that will give you Ka for the weak acid. Okay? So again, three types of problems. Finding the pH, knowing the initial concentration and the value of Ka. Finding the percent ionization, knowing the Ka and the initial concentration. And then the third one is going backwards, where we don't know Ka, but we do know the initial concentration, and we're given the pH, we can find Ka.